Hey everybody, welcome back. My name is Paul, and today we're going to be covering volcanoes, their eruptions, lavas, and rocks. Let's go ahead and jump right into this very fascinating world of volcanology. So in order to really get into this topic on the right foot, we have to ask ourselves, what is a volcano? What is it that we're actually talking about when we say volcano? We have a definition up here that I want to cover really quickly, and from there, everything else that we're going to talk about in this lecture will flow from that. So a volcano is a rupture in the crust of a planetary mass object, such as Earth. So the Earth is a planetary mass object. There are other ones in the solar system like Mars. It has volcanoes as well. That allows lava, volcanic ash, and gases to escape from a magma chamber below the surface. So this would be a large gathering of magma under pressure at some depth below the surface. A scientist who studies or investigates volcanic phenomena is called a volcanologist. Okay, so we have that down. That's somebody who studies volcanoes specifically. But a scientist who studies the conditions whereby rocks form from magma are called igneous petrologists. These are people that look at rocks like diorites, andesites, and extrapolate back the environments that created these rocks. And so many volcanologists are also igneous petrologists. So one of the things that we should recognize right from the very start is there's no single type of volcano. There's a wide spectrum of how volcanoes can behave based upon their chemistry, based upon where they're located, so on and so forth. Mount St. Helens versus Kilauea is a very good comparison. So Mount St. Helens is very well documented. It's a very important American eruption that happened in 1980. And when it erupted, it had a tremendous effect on the physical size of the mountain itself, as well as the fact it was extremely deadly. So in May 18th, 1980, Mount St. Helens erupted with tremendous force, a very large explosion. Before the eruption, the summit was 2,900 meters above sea level. So when we look at this diagram down over here, we'll actually see a couple of things. This is going to be the current summit as it looks right now. Here's the pre-eruption summit. So this is the amount of material that was here. The volcanic blast blew out the north flank of the volcano, lowering the summit more than 400 meters. So this entire part of the mountain was removed. So before 1980, it looked like this. After 1980, it looked like this. It's a tremendous difference in the shape and size of the mountain. Here we see a pre-eruption photo, and here's a post-eruption photo. This huge opening right here being where this cone used to be, the top of this mountain. Huge difference. What I'm going to do really quickly is post a video showing actual footage from the United States Geological Survey of that eruption so that you have a visualization of what this looks like. As a consequence of this massive eruption that occurred in Mount St. Helens, ash and rock debris covered 400 square kilometers and was propelled 18 kilometers into the stratosphere. This was a huge ash cloud that went straight up and then out across the United States. We could see here's the mountain. This is Mount St. Helens right here. And we could see where Spirit Lake, which was a major resort area right at the foot of the mountain, which was completely covered in ash and destroyed. Here we see the North Fork of the Toutle River, which went over in this direction, drained towards the Pacific Ocean. The net result was that trees were flattened. Mud flows carried debris 29 kilometers down the Toutle River. We'll get into what those debris flows are called a little bit later on. They're very, very deadly phenomenon. And in the end, 59 people lost their lives. It was a very large tragedy for the people that lived in this area. And it's still a volcanically active zone to this very day. It doesn't have massive eruptions anymore, but every once in a while, the earthquakes start happening. You see the steam vents kicking off. And so we know that there's activity still happening within the mountain. And here we see some of the iconic images of the eruption from Mount St. Helens, or the consequences of it. We see this forest just laid down like matchsticks, completely destroyed. Here's an eruption photo taken from the air much like the photograph, or the video that you were watching a little bit earlier. Geologist David Johnson, who was monitoring the volcano, actually gave some very good press conferences and press interviews right before about what he thought might happen with that eruption, which turned out to be true. Unfortunately, when the mountain exploded and the eruption occurred, he was killed in that eruption. This is, as far as I can tell, this is the last known photograph taken of him while he was setting up camp outside of Mount St. Helens. And of course, over here we have a memorial. There's David Johnson, as well as many other victims. All 59 victims are going to be on this plaque that occurred from the May 18th, 1980 eruption. Now, typically when we think of a volcano and we think of something like Mount St. Helens, we think of the eruption that comes out that is extremely dangerous, it's explosive, with the high ash clouds and everything that is associated with those types of events that make major news. But not all volcanic eruptions are violent, and those are the ones that don't always make news. Kilauea, for example, in Hawaii, generates relatively calm outpourings of lava, does it all the time. People go on vacation to go and see these outpourings of lava. Here we're seeing an eruption. This would have occurred on April 26th, 2022. Here we see a lava lake that is outpouring it into the magmatic system, or into the lava system that is distributing lava across the shield volcano that we have there. We'll be talking about these types of volcanoes in a little bit, but this is something that we wouldn't necessarily run away from. The camera's sitting there focused, it's pretty close, it's right there on the rim looking in at that eruption, and we recognize that this is a relatively benign eruption. The temperatures are very high, but aside from that, it's not something that people need to fear in terms of an explosion. So this is a relatively non-violent, non-explosive eruption. Now that we've begun comparing different types of eruptions, non-explosive versus explosive eruptions, we need to start looking at what causes this to happen. What is the nature of a volcanic eruption? And all eruptions involve one important component, that's magma. Magma is molten rock that usually contains some crystals and varying amounts of dissolved gases. We call those dissolved gases volatiles. They can come in many different forms. We'll be digging into what these are, but water vapor is one, carbon dioxide is another. They're very common. From magma is lava, and lava is erupted magma. That's what it is. So you will frequently hear, or scientists say, think of lava as magma that made its way to the surface of the earth. The truth is that it's devolatilized magma. In other words, the lava is separated its gas away from its original magmatic source. So you have magma that evolves into lava plus gases that have removed themselves. And that's what we're seeing here in this photograph. We see this lava flow coming through here. It's all broken up, but there's even little gas bubbles. You can see they're pulled apart and stretched apart. And we'll be digging into that a little bit, those issues in this lecture. So what is causing a lot of these differences in the types of eruptive styles in volcanoes? And it turns out that one of the places that we should look most closely is the compositional differences of the magma itself. Remember, there's three different kinds of magma. There's mafic magmas, intermediate magmas, and felsic magmas. There's actually many more than that, but those are the ones that most freshman introductory students are looking at to be able to study and to understand, and from there we can actually break out the other types of special cases that we see. Now remember what a mafic magma looks like and what it does. It's basalt, or it's gabbro, that beautiful black rock that we see up over here. That's a basalt right there, and it has the lowest silica and gas content, and it erupts at the highest temperature. So here we see the mafics right here on this chart. So the composition is mafic. Here we have intermediate and felsic. Mafic has the lowest amount of silica, less than 50%. Gas weight, or gas content, is the least of the three types. It's going to be 0.5 to 2%. It has the highest eruptive temperature. And that, it turns out, is a very important set of information for figuring out how explosive that eruption is going to be. On the far end of the spectrum over here, the felsics, these are your rhyolites and your granites. These are the most silica content, over 70%, or roughly up to 70%. They have the highest gas content, 5 to 8%, and they have the lowest eruption temperature. they could erupt as low as 650 degrees Celsius. In terms of viscosity, this is the least, intermediate, and greatest when we look at these. Now, in terms of intermediate, of course, falls in the middle between the mafics and the felsics for all of these things. So what we're going to be doing is we're going to dig into what this word is here, viscosity, because the viscosity seems to be having the largest, say, control on the explosivity of an eruption. So what is viscosity? Viscosity is a measure of a fluid's mobility. The more viscous the material, the greater its resistance to flow. So, for example, syrup. Think of maple syrup. Maple syrup is more viscous than water. Honey is more viscous than water. So here we see two fluids. Both are being poured out into beakers. This one here is flowing very nicely and easily into this beaker. And here's another one that's been poured in. In fact, it's being poured in such a way that it has a greater angle, and it's still having difficulty making its way into the beaker. So this one here has a larger resistance to flow, and therefore it is more viscous. So here we have a very viscous material. Here's a less viscous material. And the consequence is it just has a higher resistance to flow. So given that viscosity is clearly one of the biggest factors in determining how explosive an eruption is, or determining the nature of that volcanic eruption, we need to kind of dig into the factors that make things viscous or not viscous, especially in magmatic systems. So the more silica in magma, the greater its viscosity. We've determined this very early on through a lot of experimentation. The most silica-rich eruptions are rhyolites. And so here we see on this chart here, this is viscosity on the y-axis. This is over here is temperature. Here's another one with the amount of water that's inside the magma. And here's the viscosity. In both cases, the rhyolites are way up here at the top. These are the most viscous of all of the major eruptive types of lavas. Large amounts of silica, over 70%, 70% roughly, and a little bit over, okay? As we move down to the andesites, which are the intermediates, we can recognize pretty rapidly that they're intermediate, and they also have intermediate viscosity. And the same thing with basalt. Basalt is located right here, it's lower. Same thing on this chart, rhyolite, andesite, and basalt. So we know that silica content is a major control for viscosity. Also on these charts, we have temperature versus viscosity. So the hotter the temperature, the more fluid or less viscous it will be. Let's focus in on the rhyolites again. So here we have the rhyolite over here. The rhyolite has the lowest eruptive temperature of all the major types of lavas. So when we look at these rhyolites, the colder it is on this end versus the hotter on this end, we recognize that it goes through a very large range of viscosity. By the time we come over here, when it's hot, it's actually far less viscous than when it is over here on the cool end. Same thing is true of the andesites. At the andesites here, it's actually it has a relatively low viscosity, high viscosity, and then it becomes lower viscosity on this end. And the same thing is true of basalts from here to here. So temperature seems to have a large impact on viscosity, even within the same compositional range of silica. The third one that I want you to look at is the dissolved gases, mainly water vapor and carbon dioxide, but especially water vapor, because water vapor is relatively ubiquitous. It's in everything all the time in environmental systems. It's very seldom do we find purely dry rocks. So you still have a little bit of water vapor. So we're going to dig into those a little bit. And here we have water vapor and viscosity here. And we see that the rhyolites, as they move from basically pure dry rocks to about 3% water in here, what happens to the viscosity? It goes down. Same thing for the andesites. The same thing is true of the basalts. In fact, basalts can go only to about 2% composition of water, and then the water bubbles out in terms of those lavas. So we can see that these are having an effect. So if you have something that is really hot and has a lot of gases in it, it's going to have a very, very low viscosity. Okay. So now that we've looked at the characteristics of magmas that make them more viscous or less viscous, we can start to unravel what is an effusive versus an explosive eruption, what causes that to happen. in terms of our observations. So an effusive eruption is a type of volcanic eruption in which lava steadily flows out of a volcano onto the ground. It's non-explosive. What I have here is an image of an ongoing effusive eruption. There's a lava fountain that's pushing stuff out. So there's a little bit of gas that is degassing as it comes out, and that causes it to froth up and to be able to spout out some of the stuff. But we wouldn't consider this explosive. It's not like Mount St. Helens where the entire mountain exploded all in one big run. This is where we're seeing lava bubbling out of a vent and then out onto the surface. This usually involves fluid, or what we would consider low viscosity mafic lavas, right? Think of your basalts. This, in fact, is a basalt flow that is being generated by this volcanic eruption. It's caused by dissolved gases being released, resulting in expansion of magma. You can imagine that as the gas, the water that is trapped within the magma, it's dissolved within the magma. And as that magma is making its way up and it's coming under less pressure, the gas bubbles, the steam bubbles of water will suddenly be able to expand out a little bit. And as they expand, that adds some pressure upwards. It accelerates the velocity with which the magma is moving up as those bubbles start to separate out. And of course, once it hits the surface, the gases can finally escape and come completely out, and leaving the fluid magma behind, the silica and all the minerals behind. And as a consequence, lava fountains are very common in these types of eruptions. And that's what we're seeing here is a lava fountain. Effusions of lava can last weeks, months, or even years. So they can be impressive long-term events that happen in localized areas. There could be entire regions that suddenly start belching out large amounts of these lavas over very long periods of time. We're going to get into those types of eruptions here in a little bit, but this is what I want you to see in terms of effusive eruption. So in contrast with effusive eruptions are explosive eruptions, like Mount St. Helens. They're very violent eruptions, and they tend to be associated with highly viscous magmas. This is why we spent so much time talking about viscosity. Dissolved gases are released due to decompression, but tend to get trapped within the magma. So even though the pressure, unlike when we're talking about mafic magmas, the effusive magmas, when the bubbles start to form in them, the bubbles are able to make their way through. They're able to escape to the atmosphere, or to escape into a low pressure zone to be able to get away from the magma. In these cases, the viscosity has made the resistance to flow so strong that the bubbles themselves can't work their way out. All they can do is expand in place, is effectively what they can do. Or if they can migrate, it isn't very far. So further decompression of the rising magma creates a chain reaction, resulting in more gas bubbles. In other words, once you start to see decompression happening here, the gas bubbles will start to expand all around there very rapidly expanding the magma, not just the bubbles, but the entire magma, right? These gas bubbles will froth up inside of it, and the magma will then expand into a large explosion. Eruptions expel particles of fragmented lava. We're going to learn that those lava particles are actually made out of glass for the most part, and gases at supersonic speeds that evolve into eruption columns. These supersonic speeds are very similar to the physics of a cannon or a gun, right? It's all expanding gas, very rapidly expanding gas in the form of an explosion. Now, if the magma interacts with groundwater or surface water, it may generate a phreatic eruption. In other words, you add even more water, or you add something else that allows the formation of even more bubbles, the entire thing is just going to explode very violently. And in fact, that's what we're seeing here. This is a phreatic eruption. This is a column that is rising up off the summit of Mount St. Helens in an eruption that occurred in 1980. There were many eruptions that happened in 1980. This one occurred sometime after the main eruption that you've already seen video footage for. But these eruption columns come straight up. And if there's any additional water in the area that comes in and feeds into that magma chamber, you can get a large explosion like the one you are seeing in that photo. Now let's talk about the materials that are extruded during an actual eruption. We've talked about the different properties of magma and how that can generate different things. And we've done previous videos on the origins of different types of magma through fractional crystallization and things like that. And I'll link to those in the description. But we need to talk about lava flows, which are one of the major things that come out during volcanoes, right? That's the whole process, is lava extruding out to the surface. So 90% of lava is mafic lava, basaltic lava, and it erupts at oceanic ridges. It actually can erupt in many different areas, but largely at oceanic ridges. That's where 90% of it's done. About 10% of the lava is intermediate, or what we call andesitic lava. Volcanic chains along the plate margins and volcanic island arcs all are andesitic. About 1% of lava is felsic or rhyolitic lava, and it's found mostly in continental settings with hot gases and volcanic ash. And to give you an idea of the wide range of behaviors dependent, based upon the viscosity, and it's dependent upon temperature and other things. So this is a lava that is made completely out of rhyolite. It's just kind of so viscous it just bowls up. It bowls up into something called a dome, and it doesn't really flow anywhere. It just sticks right in place. Whereas basalt, just a little bit of gravitational, little bit of gravity can pull it down a very, very shallow slope. It doesn't take much. Whereas this would have to tumble down a very steep slope to be able to get moving at all in any kind of flow. So this just piles up in place, whereas this stuff moves almost like water. It's a fluid, a hot fluid moving all over the place. And you can see these behaviors in these lavas. When we are looking at different kinds of lavas, we really should focus probably primarily on the most common types of lavas within the basalts. So these would be the A'a and Pahoehoe flows. Those are both Hawaiian terms. So A'a is, even though it's just the letter AA, it's spelled with just two letters. It's got two syllables, A'a and Pahoehoe. So they're both composed of basaltic lava, the black mafic material. A'a flows have surfaces of rough, jagged blocks called clinkers. And so here we see an A'a flow moving here. This is in Hawaii. This was a fairly recent video in the last 5 years or so of it moving across a roadway, and it's burning up the local forest. The way that this works is you have a flow that looks like it's got a bunch of rubbly material, the clinkers out there on the outside. But the flow is actually still liquid and hot in the middle. And so here we see a diagram of this. Here's this hot fluid lava in the middle. And around this, it has a chilled zone. It's a little cool. It's viscous. It doesn't move as easily as the stuff in the very center of it does. But the hot fluid lava is pushing along. It's cooling down on the outside. And on the outermost part of it, it has clinkery or blocky A'a material, welded clinkers, and something called a breccia, which means broken up material. And then in front of it, it's going to be pushing along what they call the frontal breccia and talus. In other words, stuff that it's picking up, it's moving, it's pushing out of the way, or things that are just kind of conveying down in front of the lava flow. And then, of course, it moves across a basal breccia, which is the material that it's running over, those the clinkers and rocks that it's running over. And so that's what we're seeing here. This is an A'a flow, and when it crystallizes, you can imagine trying to walk over this thing. It's not gonna feel very good on your feet. And I've heard it told, and it might be true, it might not be true, that it's a Hawaiian onomatopoeia, which is the sound that you make when you're walking across it. You go ah as you're walking across an A'a flow. So that is one of the most important ones to be able to learn. In contrast with that is the Pahoehoe flow. So this is a Pahoehoe flow. Pahoehoe flows have smooth surfaces, and they can have surface textures that resemble twisted braids of rope. So here we have what we call a ropey Pahoehoe right over here. And down below we have a video showing the flow of a Pahoehoe lava flow in Hawaii. This is recent footage from the USGS. You can see it's just moving along. It rolls over itself. Here, it's just really impressive, actually, some of this footage that we have here. The surfaces are constantly regenerating, bubbling up of material, so that you can see that there's clear gases that are still within the lava, and it's making its way out. You can even see that right there in that bubbling that we're seeing there in the video. Very amazing stuff. So when magmas or lavas cool on or near the surface, they tend to contract and form fractures called joints. And I have a whole lecture where I talk about joints. I'll actually reference that in the description down below. But joints are these cracks that are a consequence of some type of force acting upon the lava. In this case, when lava cools down, it contracts. And because a lava flow can be quite large and cover a very large area, the whole thing can't contract all at once, so it contracts in segments. And when it does it, it creates these joints, and they form these amazing designs. So we can imagine that we have a lava that's cooling from the top here, the cold surface here, and it's still hot down below. And what happens is, as it's cold up here on the top, it contracts, it pulls in on itself as it cools down. And so this section of lava over here will pull away as it cools from this section of lava, which will pull in this direction and this way. It'll form these hexagonal columns. And as it cools, as it cools in this direction, the fractures or the joints will follow this seam down. It'll actually create these large, what we call columnar joints. Here we see columnar joining in the Giant's Causeway of Northern Ireland. This looks like something that was made by human beings. It is not. This is a completely natural feature that we would see in basalts of all types. We will see this in andesites. We even sometimes see it in rhyolites. So lavas will do this in general. This is columnar jointing at Devil's Tower in Wyoming. And here you can see it's coming up and all the way up to the top of this structure. This is part of what was probably a volcanic neck or was affiliated with the volcanic system there. And we could see that the lava was coming up and it was filling in this material, and then it cooled, and it cooled from the top down into this direction here. So it was hot down here, cool up here, and the cracks propagated down in this direction. This is really impressive, and it's one of the features of lavas that really stands out to anybody that studies them. Another feature pretty commonly associated with lava flows are lava tubes. They're a very important part of lava systems, especially in basalt systems, shield volcanoes and things like this. A lava tube is basically a cave-like tunnel that exists within the system, within the volcano. And they often form in Pohorhoi flows. They don't have to exclusively form there, but that's where we find the overwhelming majority of them. Lava in tubes can travel up to 30 kilometers per hour, and so the lava is really moving along pretty quick. In fact, we can see here a couple of images. Here's a skylight. Here's another skylight right here where you can see the lava is coming through here. Here's a geologist that would be able to take the temperature using something called a thermocouple. This is a very old technology. This is a photograph, I believe, from 1969 or 1970, United States Geological Survey scientists walking across this lava tube here. I always look at that with nervousness because if it failed here, what's to keep it from failing up here? But there he is walking across this. It can go at very high velocities, up to 30 kilometers per hour. And the effect of these lava tubes is that they insulate the lava flow. So while if it's not moving up on the surface, it can't interact with the atmosphere to cool down. Instead, it's inside of a rocky tube that keeps it hot, which it allows it to travel very, very long distances and can travel at pretty high speeds at those very long distances. And in fact, what we're seeing down below is a lava fire hose, is what the locals call it. Off the coast of Hawaii. This is a lava flow that is coming out of a tube. The tube is then basically injecting, or it's actually shooting the lava right out into the ocean where you can see it interacting with seawater. And you have little minor phreatic eruptions that are happening as that lava touches the seawater. So it's pretty impressive. Let's watch this for a moment. Here we could see that very, very hot basaltic lava coming in, and there's the phreatic response right there. Oh, that's impressive right there. Okay. Speaking of lavas going into water, we have to focus now on a very important structure that could be made by water interacting with lavas being injected straight into seawater. And that is that lavas, especially basalts, will form something called pillow lavas. These are formed from the outpourings of basaltic lava underwater. Remember, it's the mid-ocean ridge where we find most of the volcanism on planet Earth, and most of that volcanism is, I mean, overwhelmingly most of it is basaltic. And one of the textures that forms are these pillow lavas, frequently called pillow basalts. It's so commonly basaltic in nature that we just call them pillow basalts. What'll happen is the flow's outer skin will chill quickly when it comes into contact with the seawater, but the interior lava will continue to squeeze out and break through into another little bulb. So it'll chill really quickly and form an outer bulb. So here we can see one happening right here. So here we see a pillow that's coming out. This is now reacting with seawater, and then the middle of this is still going to stay hot, and it'll just keep punching through a new bulb here and there. And the flow is going to wind up being composed of tube-like structures stacked one on top of another. Here we see pillow basalts right here, and we can see these nice long tubes coming down, demonstrating exactly what this is. These are older pillows, or these are young pillows sitting on top of older pillows which are underneath them. This is very distinctive for basalts being injected into seawater or into water in general. You'll see these pillow basalts most frequently at the seafloor or at mid-ocean ridges. When lava flows are a little bit more viscous and they don't run all over, they can form, we talked about the clinking flows a little bit earlier, but frequently we can also get a very clinkery, blocky material when we see things that are more andesitic or rhyolitic in nature. And when that happens, we get very large clinkers, almost the size of boulders, so not small stuff, but very, very large stuff. And it's part of a lava flow, an actual moving lava flow. And this is pretty common in andesites and rhyolites. They tend to form short, prominent flows. They're very tall, they're very thick. They don't go very far, but what they do is they form these prominent, flows. Like this is what we're seeing right here. This is a lava flow we have here with big blocks of material that are coming through here. It's got a nice steep front that we're seeing here. This is going to be coming from the lava beds. It's the fantastic lava beds block lava flow in Lassen National Park. So this is a beautiful example of a block lava made of andesite. And then what we're seeing up over here is block lava flows that were erupted from the Trident volcano in the 1950s and 60s. So here we see these flows coming down, and you can see they're prominent, they're large, but they don't go very far. So in addition to lavas, volcanoes will also erupt volatiles, which is to say gases, the dissolved gases within the magmas, which make up 1 to 8% of the total weight of the magma. So there's quite a bit in there. And of course, it's compositionally dependent. We talked about this a little bit earlier, but if it's a felsic lava, it can hold up to 8%, or magma, I should say. It could be up to 8% water content or volatile content, largely water and carbon dioxide. But if it's a basaltic or a gabbroic lava or magma, it's in the vicinity of about 2%. It's much lower. So the composition plays a major role in how much gas it can hold. Now, as the magma reaches the surface and the pressure is reduced, the gases expand and escape. So we've talked about that a little bit before. Gas bubbles found within volcanic rocks are called vesicles. So here's a vesicular basalt. This is a piece of basalt. It's got some phenocrysts of olivine in it. And around here, these holes, these are gas bubbles showing the expansion of the volatiles within the decompressing magma as it rises to the surface. In this case, it was probably a lava bubbling this material out. So gases commonly associated with volcanoes include water, which is H2O, carbon dioxide, sulfur dioxide, H2S, carbon monoxide, and nitrogen gas. So there's all kinds of stuff that's going to be coming out of volcanoes. What we're seeing up there in the upper right-hand part of the screen is something called a fumarole, which is where gases are coming out of a volcanic system directly. So if it's not erupting out of the lavas, this is escaping out of another vent. And these are pretty common in volcanic systems on volcanoes, especially active volcanoes. So when you have lava and you have gases both coming out of the same vent, they're undoubtedly going to interact with one another. And they do, in fact. And when they do, you create something called pyroclastic materials, or tephra. So volcanoes eject pulverized rock and lava fragments called pyroclastic materials. And these are the result of this complicated reaction that's happening, the expansion of these gases in close combination with these magmas. Particles range in size from fine dust to sand-sized ash to very large rocks. In fact, we see a chart over here. In fact, I took my photograph off the side here so that you can see the entire thing. Here we see ash less than 2 millimeters held in this person's hand. In fact, there's a special classification. If it's even smaller than this, it can actually be classified as what we call volcanic ash. Fine volcanic dust, if it's even smaller than that. So volcanic ash is made of fine glassy fragments. This is actually caused because the magma is a liquid. It's coming out of the ground at a very high rate of speed. It's also cooling very quickly, so quickly that it cannot quench, or that it quenches and doesn't have the chance to form minerals. So the ash is actually all glass. Effectively, it's obsidian. And then we have welded tuffs that can form as a consequence of volcanic ash, which is rock composed of fused ash. So this hot ash falling all over the place, forming a blanket on top of everything, and then it fuses because it's still hot. It might be quenched to the point where it can't form minerals. The crystals can no longer form, but the ash fragments are still hot enough where they can fuse to one another. So that's what we're talking about when we're talking about ash. The next size up is lapilli, or cinders, which are walnut-sized materials. That's the stuff that we're seeing right here. This is pretty common. You see this in people's front yards. It's also used as a material for the construction of roads, for example. Blocks are the next size up. These are hardened or cooled lava that are larger than 2.5 inches in diameter. So here we see a block right down over here. This is a fairly large block. This is larger than a lapilli. If you got hit by a block, it would be very dangerous to you. So this is something that you don't want to be hit with. You could probably get hit with a lapilli if it was cool enough, and it would just be unpleasant. You wouldn't enjoy it. But if you got hit by a block, or God forbid you got hit by a bomb is ejected as hot lava. It's larger than 2.5 inches in diameter. But because they are molten to semi-molten, when it comes out of the vent, the bombs take on a streamlined shape as they hurtle through the air, and they actually wind up looking like this. So they take off as liquid, but they land as solid. They might still have a little solid in the middle of it, a little liquid in the middle of it, but this is something that comes out as liquid. It becomes aerodynamic while it's in the air, and then it lands on the ground as a solid object. So this is what we're seeing here: volcanic bombs, volcanic blocks, lapilli, and volcanic ash. Furthermore, volcanoes will also erupt rocks that have a combination of large amounts of bubbles and the rocky or the magmatic material itself. In the case of pumice, for example, which is this rock down here, we can see that it's got a large amount of vesicles. The description is white, light, gray, or pink vesicular rock, or obsidian. That means it could be a glass. From frothy, andesitic, and rhyolitic lava. In other words, it has a large amount of silica bound up within here, as well as the gas bubbles. You can see the gas bubbles are all separate. They've expanded in place. They haven't really moved a whole lot because it's a pretty viscous magma that these things are forming in. And then the other one down here, that's this rock right here. It's called a scoria. This is black or reddish brown porous rock from frothy basaltic lava. And so this is a black version of it over here. It'll come out reddish brown if there's a large amount of water or iron oxide alteration that's happening either during the eruption or due to weathering after the eruption. So it'll come up pretty reddish sometimes. So here we've got scoria. Notice that these bubbles here tend to be pretty large. They actually coalesce and they combine with one another, much more so than what you're going to see in this pumice over here, because we just have a lot more viscosity, a higher viscosity in this magma over here. Here we have 3 field examples of the tephra we were just describing. Right here is a volcanic bomb from Kilauea from 1983. We can see it's still glowing red. The inside of it is still molten. The outside part of it is hardened to a crust. And it's sitting right out here on the grass, and so it's going to wind up burning this area up as well, the area around it. These are glass shards. These are effectively ash particles, and we can see that when we look at them, they're the edges of the bubbles, where the bubbles were all together, and when they explode, they fracture out. That's what we're seeing here, are these shards. And they are very, very sharp. Very, very sharp indeed. And down here we actually have the vesicular lapilli, which is pretty common, of a cinder cone shooting out a large amount of material, all, blanketing the area right around the volcanic edifice. So while the textbook definition of a volcano is that the volcano is a fracture in the earth that releases lava and gases to the surface, we've discovered that the structure of actual volcanic systems is far more sophisticated than just that kind of textbook definition. And so what we want to do is dig into the anatomy of a volcano, what those general features are. So we're going to take a couple of slides to do that. It's really important because then it will help us understand the behavior of volcanoes, which will be the discussion for the rest of this lecture. So the general features are that you're going to have a fissure. This is a planar crack that develops in Earth's crust as magma moves forcefully towards the surface. The magma is trying to move its way up. It's buoyant, it's less dense than the rocky material that's around it, and it's trying to make its way up. So it'll rip these fractures out, or it'll follow fractures that are trying to go up to the surface. Those planar cracks can go for miles in some cases, or sometimes they're just a few meters, but for a very, very, very small event. But for a very large volcano, something like a Mount St. Helens, that could be fed by a huge network of fissures, delivering magma up into the magma chamber at the base of a volcano. So that's a fissure. A dike is when magma intrudes a fissure in older rocks and solidifies. And so we can actually study dikes to figure out how old volcanic plumbing used to work. The conduit is a somewhat pipe-shaped tunnel. When we look over here at this diagram, this is the conduit right here. So the conduit is this material that's bringing magma from the magma chamber. This is that pooling down beneath the surface and bringing it up to the surface along this conduit. The vent is the surface opening of a conduit. It's the top. It's where the volcano meets the atmosphere or the ocean, depending on whether it's in the air or whether it's underwater. The volcanic cone is the cone-shaped structure created by successive eruptions of lava and pyroclastic material. It's effectively the piling up of the lava outside of the edifice, right? The lava comes up out of this conduit and it stacks up around the outside, and it solidifies almost as soon as it comes into the cooler atmosphere or the cooler ocean. And so it builds up a huge mountain on top of this fissure that is coming to the surface. Other very important features of a volcano, and some of them are absolutely iconic, is the crater. So a crater is a funnel-shaped feature built up at the summit of most volcanic cones, generally less than 1 kilometer in diameter. So here we have a cone right here. The vent is up here at the top of the conduit, and at the top there's kind of an explosion pit where the magma is coming up, it's exploding, it's separating out the lava from the gases, and it's coming out the top of the volcano. And it's generally less than 1 kilometer wide. And we would find that crater usually right up at the top. We can find, by the way, craters anywhere where this is happening, but generally there's a large one at the top. A caldera is a large circular depression that generally has a diameter of larger than 1 kilometer and is produced when the summit collapses. So this is a different type of edifice. This is a different type of way that the magma is coming out and the way that the volcano is behaving. There is not a caldera depicted on this image, so we're going to come back to calderas in a few slides. Parasitic cones is a flank vent that emits lava and pyroclastic material. Sometimes it's just easier for the volcano to emit stuff out the sides. So here we might have a parasitic cone, a small volcano on the side, where it's just, it's obviously it's easier gravitationally to go off to the side than it is to go all the way to the top. Even if there's a path of least resistance to the top, gravity just might make it easier to go to the side. And then there's fumaroles, which are a flank vent that emits gases. And so fumaroles are where you get your hot springs, and you get bubbling out of gases and things like this that are associated with fumaroles. We'll be talking about those quite a bit later. A great way to understand the complexity of the plumbing that's going on within a volcano is to look at a picture of a place like Mauna Kea, which is one of the large volcanoes on the Big Island of Hawaii. It's right next to Mauna Loa. And what we're seeing all over this structure here is, here's the peak, here's the top, where all the lava flows originally were flowing out, but now it's dotted with all these parasitic cones. These parasitic cones are all over the place. There's dozens and dozens of them, and in fact this image doesn't even come close to capturing all of them. Many of these large volcanoes, in this case Mauna Kea, Mauna Loa has them as well, they're all over the place. So you can imagine that we have lava pockets that are within this volcano that are finding easier paths out of the volcano than out of the main vent, out of the top, just to show and demonstrate what's going on here. So now that we've covered all of that material, it's time for us to actually dig into the volcanoes themselves. And there's different kinds of volcanoes dependent upon the kinds of lavas that are coming out of them, the composition of the magma. I mean, you can see that we were leading up to this. The first place we're going to start are with the biggest and most magnificent of all volcanoes on planet Earth, and probably in most of the solar system, shield volcanoes. General features of the shield volcanoes are that they are generally broad, slightly dome-shaped features. They kind of imagine this. This is a schematic of an island that would have been formed from a shield volcano, kind of similar to what we would see in Hawaii. We see this kind of shield, like a Roman shield, laying on the ground. It's produced by the accumulation of low viscosity basaltic lavas. Remember, low viscosity means it's free-flowing. It moves very, very easily. And so, as a consequence, when the lava erupts from the top, say out of a lava fountain, there might be a little bit of tephra, a little bit of ash and gas, but not a ton of it coming out relative to what we see from the other types of volcanoes where that's more dominant. What we would see coming out of here is lava effusing out the top. It would come out and cover very large areas because it's very fluid lava that can go very long distances. Many of these very large volcanoes, these shield volcanoes, begin on the seafloor as seamounts. Only a few, though, are large enough to form a volcanic island. In other words, they start to grow, and then some process, the magma source moves away through plate tectonics or something like this. Very few actually make their way all the way to the surface to form an actual volcanic island, but when they do, they're pretty spectacular. Classic examples of shield volcanoes include the Hawaiian Islands, the Canary Islands off the coast of Africa, the Galapagos Islands off the west coast of South America, and Easter Island as well in the Pacific. Mauna Loa is the largest volcano on Earth, and it is a giant shield volcano. And it looks very similar to what we have here with this shield, the lava flows coming down, eventually entering into the ocean. And once there's an ocean entry, we have a plume of material that is produced there. It also has nice pahoehoe flows that are coming down the flanks of the volcano that sometimes produce very large breakouts. Sometimes those breakouts, which come out of the lava channels, those breakouts could also come out of lava tubes, or even eventually even dump into lava tubes. So you get these complicated going back and forth of lava. As it's coming down, it'll go into a lava tube, it'll break out, it'll drop down into another lava tube, it'll come out of a lava channel. And I'll show you some images of lavas moving and behaving in this way. And of course, famously, in a place like Mauna Loa, it'll wind up in the ocean, forming very large and sometimes explosive entrances into the ocean, where the ocean is flashed into steam. You might have a certain degree of phreatic reaction that's happening there, and it's just spectacular. This is what we see here with Kilauea and Mauna Loa. They're both kind of tapped into the same hot spot within the center of the Pacific Ocean, or underneath the Pacific Ocean, in the mantle. This hot spot is feeding magma up into Mauna Loa. It's also now feeding it up into Kilauea. There are shield volcanoes that are nested one on top of each other. And what's happening is the Pacific plate is actually moving in this direction, and as it moves, the hot spot is not moving relative to it, or it's staying relatively stationary. And so, as a consequence, Mauna Loa is being dragged across this hot spot. It's being fed right now, and Kilauea is starting to be fed, or has been started to be fed more recently. And so that will become the more dominant shield volcano over time, and then eventually it will fade out and something else will replace it. And here are those features on Mauna Loa. We see the peak of Mauna Loa right here, this very wide slope coming down here, showing that we have lava not only emanating from here, but there's actually a fissure that runs right along here. It's called a rift. That fissure has lava that's spilling out. It's effusing out of there and feeding these lava flows. There's actually a set of parasitic cones that are also right along these flanks. But you can tell there's the classic shield volcano, and this thing is just massive. The top of the tallest mountain on Earth, if you measure it from base to top. As I said earlier, Kilauea is now on-ramping and replacing Mauna Loa as the active shield volcanic system in the area. They're both quite active, but Kilauea is much more active. It's continually active. In fact, Kilauea has been Hawaii's most active volcano, and it's one of the most active volcanoes on planet Earth and has been for several thousand years, for sure. On May 3rd, something pretty spectacular happened, in May 3rd, 2018. Multiple fissure eruptions sent lava flowing into the streets of many Hawaiian communities on the flanks of Kilauea. And for the next month, several subdivisions were not only heavily damaged, but some of them were completely annihilated by the outflow of these fissure eruptions. And about 600 houses and other structures were destroyed. And here we see images of the types of lava that were coming out of those fissures, and some of them were actually coming out of local cinder cones. We're going to talk about cinder cones. But these lavas that were coming out were just flowing very fluid and very high speed. And honestly, there's nothing you could do to prevent them from running into a neighborhood and causing a tremendous amount of damage. There's an alternative type of volcano that is basaltic in nature called a cinder cone. They're relatively small, they have a lot of gas in them, and while we frequently call them cinder cones, the proper term is actually scoria cone. But the common vernacular, what just everybody refers to them as cinder cones, they're built from ejected basaltic lava fragments, stuff that's being erupted into a pile. Unlike a shield volcano, which has a very, very low angle where the lavas are flowing very long distances, cinder cones basically shoot this material out like almost, I always use the analogy of like a popcorn machine, piling up big amounts of lapilli, large amounts of cinder, scoria, all around its flanks, and it has a very steep angle. They're comparatively small in size compared to all the other volcanoes. They could be between 30 and 300 meters tall. And the big one is about 300 meters tall. It's about as big as they get. They frequently occur in groups. This is a pretty common feature of cinder cones. In fact, when you recall that image I showed you of Mauna Kea earlier, you'll notice that it was a big group of cinder cones around the top of the top of Mauna Kea's summit. So it's not uncommon to see that. There's frequently a well-defined crater up at the top, and they're usually associated with extensive lava fields, but these generally form in the final stages of the volcano's lifespan. So that's when you start to see, the lava trying to find alternative ways out. There's just a little bit of residual material with a lot of gas in it, and it'll form these cinder cones along its flanks or up at the top as it's expiring, that volcanic system. And to demonstrate a real cinder cone in the field, one of the best places to look is Sunset Crater in Arizona. Here we see it, nice crater up here at the top. We can see that the tephra has been thrown out. This is mostly lapilli. There is a lava flow on the backside of this, and I visited that lava flow. I have a video where I'm looking at the types of rocks at those lava flows, and I'll link that in the description. But this cinder cone here is part of a larger cinder cone field, a volcanic field that we see over here in the background. These are older, not volcanically active. They're extinct at this point. Older volcanoes back here that are now starting to become deeply eroded, as what will eventually happen with Sunset Crater. Now, when most people think about volcanoes and they want to draw a picture of a volcano when they're young people, Generally speaking, they draw a composite volcano. Composite volcanoes are those tall ones with the fire coming out the top and the whole thing. The general features of a composite volcano is that it's large. It's what we call the classic shaped volcano. It's got symmetry about it. It could be thousands of feet high, several miles wide at the base, like what we're seeing right here. In fact, this is the same volcano. And the way that this works is it's composed of interbedded, which is to say generally andesitic lava flows, interbedded flows, and layers of pyroclastic debris. So in other words, it'll have a lava flow and then tephra. Lava flow, tephra. Lava flow, tephra. And it creates those layers. And as a consequence, we also can call them stratocones, which means layered, right? These are layered volcanoes. And so here we see the same volcano. This one here is emitting effusive lava. So it's making a layer of lava in 2009. But we have a history of this same volcano in 1984 doing an explosive eruption, leaving pyroclastic material across its flanks. And so it's that layering that defines these types of volcanoes, these composite volcanoes. And here we see an eroded outcrop of a composite cone in Oregon, and we can clearly see that we've got lava flows. And then above this right here, this is our tephra. This is our pyroclastic material that's been deposited across the top of it. And what we are seeing here is lava, tephra, lava, again, more tephra and pyroclastic material forming these layers that are moving out towards the edge, the outer edge of that volcano. So the volcano is just built up layers of these eruptions. And that's what defines these very large, massive, eruptive andesitic volcanoes. So we mentioned these a little bit earlier, calderas, as being kind of an alternative to craters at the tops of volcanoes. They're formed in different ways. And so I want to make sure that we get our definitions correct. So a crater at the top of the volcano is due to explosions. It's gas separating out of the magma explosively and removing the material and the debris out of the top of it. That's an explosion that's happening here. A caldera is actually formed in a different way. So first off, what is a caldera? So a calderas are circular, steep-sided depressions with a diameter of larger than a kilometer. Now that's actually the part of the definition that we actually need to probably push to the side a little bit as being less important, is the greater than 1 kilometer. What's really important is it's a depression as opposed to an explosion pit, right? So it turns out there's 3 different types, and the size of 1 kilometer or larger is coming from the fact that we just recognize that generally they're a kilometer or larger. They're not defined that way. So there are 3 major types, and it's based upon, as we've been talking about the whole time, the composition of the magma that is producing the volcano. So they're the Hawaiian type calderas, which are going to be basaltic. In fact, here we see a caldera. This is that depression that we're seeing right at the top of Kilauea. There's crater lake type calderas. So Crater Lake is a major andesite volcano, part of the Cascades Range in Oregon. And here we see Crater Lake right here. The caldera is actually this circular part right here. It's not this volcano in the middle. This is a different type of situation that's happening here. The caldera is this right here. And in this case, the lake is 8 kilometers wide, and that's the depression that is settled in. And for rhyolite, that would be the Yellowstone caldera. So a very high silica amount, very viscous type of magma is going to produce a very large caldera. And when we look here, we say, I don't see the caldera. Well, the reason why is the caldera, instead of being 8 kilometers or 1 kilometer, is, as we see in the case of Hawaii, it's 50 by 75 kilometers. It's enormous. It's so large that you can't take a photograph of it. All we can do is take a photograph of the rim of it. And that's this range of hills and mountains over here on the edge. That's the edge of the caldera. It's kind of like looking at what's over here on the side. Yellowstone calderas are enormous. So let's start talking about what a caldera is in terms of how it functions in a volcanic system. And the best way to look at this is to look at Hawaiian type calderas, because that's what we really know well. We've seen these in action. We understand them pretty well. And so we're going to start there. So Hawaiian type caldera is where the floor is bounded by ring faults. Ring faults. So a fault is a fracture in the earth where movement is happening between rocks. So there's ring faults or dikes above a magma chamber. So here we have a magma chamber, and then above it is our ring fault, right? So here we have our caldera, here's our depression. It's almost like a giant piston, right? And so these basaltic dikes, which are feeding in the basalts into the magma chamber, it settles it to the bottom of the magma chamber. There's this material sitting up on top of it that can actually move up and down. In the case of a depression, it's going to drop down, which is why you see it like this, and it's going to create this ridge that we're seeing up here on the top along the ring fault. So all active calderas may have lava lakes within them. So this here can actually then feed lava that will then move across the top here. And so when we look at Hawaiian type calderas, what we're seeing here is here's Kilauea, here's the caldera up on top. There's going to be a very deep lava tube that's going to be feeding the system. So underneath this caldera and this magmatic reservoir is responsible for all of the material that we're seeing through these lava tubes and out into the ocean and on Mauna Kea, Hawaiian type eruptions. And all of this is going to be operating like a giant piston. So if there's any type of blockage that's happening up over here, you would expect to see that Kilauea caldera is going to respond. It's either going to move up or down based upon that. And in fact, when the chamber is continually filling and rising, we call that inflation. And then if the magma is coming out, it'll cause deflation. In other words, the floor will drop. Crater lake type calderas form in a slightly different way. I mean, many of the structures are the same. You still have the ring faults and stuff that you see in the Hawaiian type calderas. However, the crater lake type calderas occur when we have a very large composite cone that then erupts. So we can actually follow this in this diagram right here. You can imagine we have a composite cone located right here, and the magma chamber's at depth, and here are the feeder dikes that are bringing the material up to the top, the conduits and all of this. And what happens is when that material comes out of the volcano, it evacuates some of the space down below within the magma chamber. And so what happens is that as the eruption occurs, it deflates the entire summit to the point where we have a newly formed caldera. A set of ring faults might set up around here, forming those nice ridges. The entire summit volcano will then settle within here and then begin to accumulate rainwater or groundwater into the system. It'll actually trap it within that caldera. And you might even, in the case of what we see at Crater Lake, you might even have a little bit of a subsequent eruption that will produce a secondary volcano within the caldera that pokes up. And that's what we're seeing here. This is Wizard Island, which is a secondary volcano. It's nested on top of the conduit, and it's bringing in new lava flows and new eruptions. However, it's not so much that it can push out the water in the area. So here we've got Wizard Island again right here, but the main caldera is located here. And this is a pretty standard form of andesite caldera that we see when that type of collapse occurs. And there's several examples, very good examples, other than Crater Lake throughout the world. So it's not just like Hawaii, where Hawaii is pristine and perfect, and there are other volcanoes similar, but nothing comes close to Hawaii. It turns out there are quite a few others, and we actually have some images here. And here are those images. Here we have one in Cambodia, another one in Costa Rica, another one in Indonesia. Here in the one in Cambodia, we can clearly see the crater right here, but it's actually not a crater. Remember, it's a caldera. It's a downdropping. And then here we have in Indonesia, we have, just like Wizard Island, we have new lava that's coming into the system up probably along one of those ring faults, which is why it's nested over here on the side. But the rest of this depression is the caldera right here, where it's dropped down. And same thing in Costa Rica, where we see it's dropped down into what used to be a much larger volcano. In contrast with both the Yellowstone and the Crater Lake type calderas are the Yellowstone types. These form from the collapse of a very large area, not just the volcano above it, but the entire region in the area after the discharge of large volumes of silica-rich pumice and ash. These calderas tend to exhibit a very complex history. In fact, this is usually the topic of many volcanology courses and igneous petrology courses in upper division coursework for geologists, working out those complex relationships in the complex chemistry. Many calderas exhibit something called resurgent domes. This is where there's a failure, but rather than have a new volcano pop up like a wizard island, instead the lavas will start to bulge up in the middle of the caldera, almost like underneath a blanket of ash and material up on top. And these here we see in the outline of the caldera. This is Yellowstone caldera right here, and here are those resurgent domes right here. The eruption that produced this caldera originally has created something called the Lava Creek ash bed, and it's massive. So here's the Yellowstone caldera located here. This is the mapped extent of the Lava Creek ash bed. So this was a massive eruption when it erupted some several 100,000 years ago. All right, so now you should have a pretty good grasp on how volcanoes operate, how the plumbing system seems to be working, how the caldera system is working, and what occurs when magma reaches the surface. Let's start talking about some of the major hazards that come from volcanic eruptions, the eruptions themselves, right? And the most iconic of all of the hazards that we deal with for volcanoes are pyroclastic flows. So a pyroclastic flow is a high density mixture. So it's a slurry, or it's an airborne slurry of hot gases infused with incandescent ash. That means it's hot. It's hot, and it could even be glowing. With incandescent ash and larger lava and pumice fragments. So it's going to come out fast, it's going to come out hot, it's going to be glowing. It could also be called a nuit ardente, which means glowing clouds in French. It's propelled by gravity and moves similarly to snow avalanches. I have a lecture on that talks about that in my landslide lecture. So if you are interested in how avalanches work, make sure you check out that lecture on landslides. The material can also be propelled from the vent at high speeds, over 100 kilometers per hour. And pyroclastic flows are typically generated by the collapse of tall eruption columns. So this is a big slurry, a mass of glowing hot rock, ash, and air coming down the volcano. It's formed from the collapse. And remember that big blast that goes up into the air. Well, what comes up must also come down. And this is something you don't want to be coming into any type of contact with. Here's a pyroclastic flow at Mount St. Helens. This is all pumice that has come down here. We'll be showing you an image of the pumice plain shortly. Here's another one. We've been showing pictures of this volcano previously. This is a composite cone with a beautiful pyroclastic flow coming down. And of course, if this was to hit you, you would be incinerated instantly. You'd become an instant death victim. In contrast with a pyroclastic flow is a pyroclastic surge. These are relatively safer. They're still extremely dangerous. They're low density currents that usually separate from the main body of the pyroclastic flow. So as a flow is moving downhill, the lighter density stuff will float to the top, and it can actually take its own trajectory. It can go its own direction if it wants to. Occasionally, these surges have enough force to knock over buildings and move automobiles. They're a serious problem. This is a pyroclastic surge that we're seeing in the Soufriere Hills volcano in Montserrat, which was a major eruption that happened in 1997. And they can go very long distances. They blanket everything with ash. We've talked about how dangerous ash is. And it also could be, it can be hot enough where it's a serious hazard. So these pyroclastic surges are not a joke either. And we can see the examples of how pyroclastic flows and surges operate just by looking at a geologic map, a basic schematic map, but a geologic map of what we're what happened at Mount St. Helens when we had the major eruption that happened. So this entire area was excavated from, this is the old summit. This material erupted laterally, in other words, it went sideways. It came straight this direction towards Spirit Lake. It went across the pumice plain, which is where all that pumice was being settled in. I just showed you a picture of that pumice plain. And then it went across the valley and it actually started going back uphill. And they call that the run-up. So even if you were on the other side of this valley when this eruption occurred, you were likely to become a victim. In fact, we talked about geologist David Johnson and his unfortunate passing as a consequence of this eruption. He was situated right over here. In fact, Johnson Ridge Observatory, which was built to commemorate his work and to commemorate his life, was constructed right here. This is an observation deck that looks into Mount St. Helens. Was constructed right here. And so you have an idea of where he was approximately when he was killed. Over here we see a major landslide deposit that was also created by the eruption. That landslide deposit came down and created these things called hummocks, which are hills in the area. This is something not created by rivers or anything like this. This is what this eruption does. It dumped all this material up the other side of the valley and scoured it all out with very hot, very dangerous material that was completely unsurvivable. So the creation of a large amount of tephra, pyroclastic flows, things that are ejected into the environment around the volcano during massive explosive eruptions, like what we would expect from an andesitic or a rhyolitic eruption, is going to create a whole new classification of rocks that we call the pyroclastic rocks. What are pyroclastic rocks? Well, these are rocks that are made of consolidated or welded deposits of volcanic ash, tephra, and other volcanic debris. A rock formed this way is called a tuff. That's the generic term for the material that is thrown out, especially if there's a lot of ash in it. Tuffs form either by fallout, which is ash fall. In other words, the ash comes up and then it falls down and almost like snow on top of everything, or it winds up in the pyroclastic flows and surges that come off the volcano during the eruption. If they are still hot enough, that being the tuffs or the deposits, when deposited, the ash particles fuse or weld together to form a welded tuff, which is a very coherent, hard rock. Another type of rock that I want to bring up is something that we call ignimbrites. So ignimbrites are formed by widespread deposition and consolidation of high-density pyroclastic flows. And what we see here is a couple of examples of ash flow tuffs. This one right here has got rock fragments in here, it's got pumice fragments in here, and that white material is formally ash that is slightly fused together, holding it together as a coherent tuffaceous rock. Down below is a welded tuff where you can see that the heat has actually caused everything to collapse and fuse together. We see these thin streaks that are moving through here, which are materials that have been consolidated down in the heat and compressed. This is an extremely hard and as well as informative rock because it tells us something about how hot that pyroclastic material was when it came out of the volcano and deposited. Now I want to take a quick minute to talk about what tuffs look like in nature. They don't look like regular lava flows or even granites or anything like this. They're very, very different. They're unusual, and usually when people see them, they don't know what to make of them. They look like something otherworldly almost. So what I want to do is bring up the example of what we see in the Bandelier tuff. It's a very well-studied tuff, and we'll explain why here in a moment, why it's so well known. But what it is a tuff, and here we see an image of it right here. It consists of a series of thick ash flow tuffs that were erupted from the Valles and Toledo calderas. This tuff weathers to form a Swiss cheese type of surface. And by the way, this isn't just unusual, or this is not unusual for tuffs, the Swiss cheese appearance. And here we see it right here. Right, this is that Swiss cheese appearance that this text is talking about, with pockets in the cliff face called tuffoni. So that's what these little pockets are that we're seeing in here. The non-welded lower section of this ignimbrite, so here we see this ignimbrite right here, is soft. So it's not welded. It doesn't have all the fused ash particles in there. And so it turns out that this made an unusual opportunity for the ancestral Puebloans who lived in the area, who enlarged the Tafoni and excavated chambers cut in soft rock to be the interior rooms of their cliffside pueblos. That's what we're seeing right here. They're actually have excavated this area and moved into those holes because the rock gives sufficient coverage. It's strong enough to be able to keep them safe, but at the same time soft enough where they're easy to quickly excavate into it and make it into a nice environment in which to live. So you can't really mention volcanic hazards, especially explosive volcanic hazards, without discussing a phenomenon referred to as a lahar. So a lahar is a mud flow on an active or inactive volcano and is one of the most feared of all natural disasters. And it's feared for many reasons, but mostly because it can reach very long distances with almost no warning. Lahars are triggered when magma nears the surface of a volcano covered in ice and snow and causes it to melt. Volcanic debris becomes saturated with water and rapidly moves down a volcanic slope. Here we actually have a photograph. This is Mount St. Helens again. I keep using Mount St. Helens because I want you to understand these features are all associated with it. Mount St. Helens, this is a lahar that happened in 1983. It's a relatively small one after the main eruption about 3 years later. During the main eruption, there were several lahars that were generated that did immense amounts of damage up and down the Toutle River, which is off in this direction here. In fact, this lahar melted this zone right here, ran down, part of it went into Spirit Lake, but most of it wound up into the headwaters of the Toutle River. So when Mount St. Helens erupted in 1980, several lahars were generated. Rocks made from lahars are a form of sedimentary rock. So here we see a lahar deposit up in the Cascades Mountains range. I'm not sure exactly which volcano made this one, but here we can clearly see the material is large. It's very violent, whatever the slurry is that's bringing it in. It's got a lot of mud, it's got ash, it's got tephra, it's rounding stuff in here. And of course, if a human being or an animal or a vehicle or a car or a house was to get caught up in one of these types of flows, this is what you're being hit by. This is not just a bunch of mud. This is boulders, rocks, and cobbles that are just tearing things up, and as they move down these river valleys at very high velocity. And frequently, the flows themselves are actually hot. They're not even cold, like a cold torrent. It's actually hot water that's running down. They're terrifying events, not only to see on video, but based upon eyewitness testimony that we've received that you can find online. These events are just terrifying, and people never forget them. And there's several other volcanic hazards that we need to make sure that we are aware of that governments worldwide keep track of. So there's, for example, volcano-related tsunamis. I bet you didn't realize that there were tsunamis frequently affiliated with volcanoes, but there are. And of course, a tsunami is a destructive sea wave that can form after the collapse of a volcanic cone. This happened in Tonga in 2022. Volcanic ash that winds up getting up into the atmosphere can be a hazard to airplanes. Jet engines can be damaged when flying through a cloud of volcanic ash. In fact, there was a famous episode of this in 2010 when an Icelandic volcano erupted and blocked flights between North America and Europe and blanketed ash all over the place. It actually did damage to a lot of military aircraft. Most civilian aircraft were grounded at that time. And of course, there's volcanic gases that can be emanated, not only just during the eruption, but just simply it's being put out by the volcanic processes through the plumbing. So volcanoes can emit poisonous gases, endangering humans and livestock. And so when we look at what a volcano can do, here's our conduit. It produces earthquakes. It can have a giant landslide, right? When you oversteepen the flanks of that volcano. Pyroclastic flows. If you've got a prevailing wind, that eruption column is going to come up, create an eruption cloud. You're going to get ashfall. You're going to get more pyroclastic flows, possibly a lava dome, which is going to suddenly hang out over the landslide and possibly, the landscape, and possibly slide down into that landscape and be a problem. There are many volcanic hazards, and they have to be monitored very, very carefully. Some of them are relatively benign. Some of them are harbingers of major problems, and we need to watch these things very carefully. So beyond volcanoes themselves, there are other volcanic landforms that exist on Earth that meet the definition of a volcano. Remember, a volcano is simply a fissure, a planar fissure that is carrying magma. It's a conduit for magma to the surface of the Earth. And so if we look at this, we discover that there's other volcanic landforms that we probably need to talk about really quickly. And some of them are major features on planet Earth. So fissure eruptions and basalt plateaus are a real big deal, especially when we look at the history of Earth. So fluid basaltic lava, remember, basalts are really low viscosity, so they flow a very long distance, but these are especially fluid. Extruded from fissures blanket a large area called a large igneous province or basalt plateau. Let me give you an example of what we're talking about. So here we've got some fissures in the earth. Here's a fissure in the earth right here. This one has got an eruption associated with it. This one does not. This, in fact, is a point where there's probably a lava fountain that had developed, which was having an effusive eruption. But here we can see it's running all over the place and covering the entire landscape through this zone here. That's what we're talking about in terms of that fluidic basalt that's coming straight out of a fissure. There's no cone here, right? It's just coming right out. This is still a volcanic landform. When this happens, we get the term flood basalts. So flood basalts appropriately describes these eruptions. And there's two very famous examples. The Columbia Plateau and the Deccan traps are two examples. So this one's in India. Of course, this one's up in the northwestern part of the United States, mainly in Washington and Oregon. In fact, when we look at a map of the Columbia River flood basalt province, we realize that we have a pair of we have several swarms, but we have a dike swarm located right here, a large dike swarm located right over here, another one up over here, and some back here, and then we have this huge province, all in yellow, of where these flood basalts are, and they're associated, of course, with the dike swarm. Another important volcanic landform to know about is something called a lava dome. So a lava dome is a small dome-shaped mass composed of rhyolitic lava. So as viscous lava is squeezed out of a vent, it produces a dome-shaped mass. Remember, rhyolites are very, very, very viscous. They have a high resistance to flow, so they'll ball up before they'll start to move like a basalt will. Basalt will flow very nicely. A rhyolite won't. It'll come out, it'll stick to itself, it's just not going to move. In fact, when we look over here, it says it's directing us to look over here at A. A is right there. So that's this lava dome right here in the middle of Mount St. Helens. So this is where lava has come up. It's too thick to flow. I'll just use the common vernacular. It's too viscous to flow, but it's too thick to flow is how many people think of it. And it's not going to move down easily. And what can happen over time is it's just going to sit there and grow and grow and grow as more lava punches in from below. So collapse of lava domes often produce powerful pyroclastic flows, as shown here in B. That's what we're seeing here. So the lava domes are rising, and what will eventually happen is they'll get so tall that they'll oversteepen and they will gravitationally fail. They'll act like a landslide. And of course, as that moves down, the magma that is hot underneath it will suddenly become exposed, and that can even erupt out from behind it. And so you can even get a pyroclastic flow coming from behind, as well as the debris avalanche that's going to be coming down the valley from the lava dome that we're seeing right here. Now, this differs from a resurgent dome in that it is extrusive. Remember, in a resurgent dome, the situation was the lava was punching into the magma chamber, or punching up from the magma chamber below the caldera. In this case, it's actually pushing its way up and out. It's actually extrusive and made its way out of the volcano, out of the edifice at this point. And there's no way that we could talk about volcanoes without explaining how we know what the plumbing inside of a volcano looks like. This is by studying largely volcanic necks. So a volcanic neck is the remains of magma that solidified in a volcanic conduit. So Ship Rock in New Mexico is a famous example of this. This is Ship Rock right here. Here's the conduit. Its remains are still sitting there in the middle of the desert. And here are the fissures, right? The dikes that were feeding this system in here. All this magma was distributed and coming into this conduit and then up theoretically into some volcano that was above it. That's what we're seeing here in terms of an interpretation, that there was a volcano originally quite high up. There was this conduit that was filled with rock and magma that was feeding that volcano. Yet today, after the volcano has long ago gone extinct and the entire region has stopped being volcanically active, at least as related to this particular event, there's been a lot of erosion, and that erosion has revealed the deep inner workings of this volcanic system. That's what we're seeing here at Ship Rock. This is still a huge peak right here, 1,700 feet, just of the conduit throat that we still see from that ancient volcano. Another amazing volcanic landform to know about are these things called volcanic pipes. Volcanic pipes are a rare type of conduit that originated in the mantle at depths exceeding 150 kilometers. So this is something that is tapped way down deep inside of the earth. This is a volcano that is getting its magma source down very, very deep. A classic example of this would be a kimberlite pipe. Kimberlite pipes are extremely important because this is where we get diamonds from, for example. So when we look at these things, for example, economically important xenoliths, this is a new word. A xenolith is a rock or material that is actually derived from deep beneath or from outside of the volcano. So it could be maybe a part of the wall rock that we're seeing, or something deep down inside the earth that is being plucked up and being brought up with the volcano. So these economically important xenoliths are often associated with them. So here we see a diamond that has actually been collected out of a volcanic kimberlite pipe. This is a deep, when I say very deep, I mean it's actually down probably from the mantle deep, diamond that has been pulled up during the volcanic eruption and is now available up here at the top. And don't worry about these other things that we have here in terms of these things. The main thing is that the pipe is tapping into the root of the mantle, pulling this material out. Xenoliths of diamond-bearing upper mantle rocks. So there's diamonds in here, and the volcano is bringing them up to the surface in the forms of xenoliths, little rocks that are pulled up in these pipes. When volcanic activity begins to interact with groundwater, there's a really good chance you'll start seeing hydrothermal features start to develop around that volcanic system. And when we talk about hydrothermal features, we're talking about geysers, hot springs, and fumaroles. These are all associated with something called subaerial volcanism. Subaerial means in the atmosphere. This is in the atmosphere, as opposed to submarine, which is into the water, or maybe rocks or eruptions that would be going into space. This might occur on an extraterrestrial body, for example. A geyser is a spring characterized by intermittent. That means it happens on occasion, right? It's not happening all the time. So there's not always water and steam coming out all at the same time. It'll come out in bursts. Intermittent discharge of water and steam ejected turbulently, okay? When we look at what a geyser actually looks like, one of the best places to go is to look at a cross-section of what's happening at Yellowstone Caldera. Here we see a geyser idea where we have hot rock. This is rhyolite down here. We know it's getting hot because here's the temperature as we go down into these glacial gravels. So effectively, since the last time there was a major eruption and this rhyolite was extruded into this area, glaciers had left gravels across the top of this. So in these glacial gravels, there's a large amount of groundwater circulating and moving around. The Yellowstone River, for example, is constantly making sure that the entire area is topped off with water. So what happens is you have this hot rhyolite down here, a temperature of 180 degrees Celsius, all the way up to just below the surface, it's still over 100 degrees. So at 180 degrees to 100 degrees, we all know that water wants to boil at those temperatures. So 100 degrees Celsius, remember, is the boiling point of water. So on this diagram, from about this point down, all of this water is under pressure to boil. It's trying to do that phase transformation from a liquid to a gas. And what we have here is And of course, it's under pressure as well, so there's some restrictions on what's happening. But we have hot water down here at the bottom, cold water up here at the top, and one of the things that we know about hot water is that it wants to rise. Anybody who's ever boiled a pot realizes that the hot water at the bottom of the pot rises to the top, and the cold water at the top falls to the bottom. And so what will happen is the water will start to move into this plumbing, into these holes and into these conduits, and they'll get trapped. And what will happen is the water that is trapped in here as it's trying to make its way up here and through these restrictions will begin to boil. You'll start the formation of bubbles. You'll create bubble traps. And effectively, you'll build the pressure up. It'll start to rise. And eventually, these bubbles will overcome the amount of water that is sitting on top of there in terms of pressure. And the bubbles will push the water out. And when that happens, you have a geyser ejection. Right, so here we've got a geyser with liquid and steam coming out, and then once that's done, that water that's up at the top will then circulate back down in, or it'll recharge in from the groundwater, from the gravels, and it'll reset the entire system. And so that's how a geyser works. A hot spring is produced by the emergence of groundwater that is heated either by shallow bodies of magma. What we're seeing here is here's our glacial gravels. This would be where we'd have the water coming straight up. The water is going to just kind of boil right on out of the top, and it's not going to come out in a turbulent eruption. It's going to be a constant trickle that's going to be coming out. In terms of a fumarole is a vent from which hot volcanic gases and vapors are emitted without any liquids or solids. So this is where the gases are coming out in the form of steam. There might be degassing of the actual rhyolite. Any gases that are trapped down here will be able to make their way out. Now, if you have a fumarole with any fine-grade solids, maybe a little bit of liquid that happens to be in the area, you might actually create something called a mud pot. And so I'm going to go ahead and show you a couple of videos of these types of features, just so that you know what they look like in nature. It's very important that we connect what we know about volcanology to our current understanding of plate tectonics. If you recall that plate tectonics is the unifying theory of geology, and it explains the way that the Earth's surface is evolving over time. And so volcanoes, of course, are a major agent in this change. We have to recall that plate tectonics tells us that there are plates that are relatively independently moving around on the surface of the Earth in response to heat flow and mantle convection and things like this, and that the plates at the surface can move one of three ways relative to one another. They can move into each other. We call that convergence, and when that occurs, one plate will dive beneath another. So that is a convergent plate boundary. They can move away from each other. That is a divergent plate boundary. Or they can move side by side. When that occurs, that is a transform plate boundary. Volcanism happens extensively along divergent plate boundaries primarily, and then there's a huge amount of volcanism that occurs with convergent. A lot less of it is associated with transform plate boundary. It does happen, but we usually deal with that on a case-by-case basis, and so that's kind of beyond the scope of what I'm going to talk about here. But what I want to do is connect divergent plate boundaries to the volcanism that occurs there, because overwhelmingly, the greatest volume of magma erupts along divergent plate boundaries and is associated with seafloor spreading at mid-ocean ridges. In other words, the volcanoes are happening exactly where plate tectonics expects the volcanoes to happen, right? There's partial melting of the upper mantle, that material rises to the surface, and it winds up in these volcanic flows. It ejects itself into these fissures and rises up to the seafloor. And as the seafloor is spreading apart, those fissures open up, the magma is injected into it, into the form of lava flows up at the surface when they finally make their way out. There's going to be complicated interactions between the magma chamber at depth, these fissures, and seawater that's going to be coming in. We'll be spending a little bit of time talking about that here in a moment. This is characterized by vast outpourings of very fluid basaltic lavas. So basalt is what we're talking about at the seafloor. These very, very large provinces of mountain ranges, mid-ocean ridges that are pouring out 75% of Earth's total magmatism. These lavas are called mid-ocean ridge basalts. We call them MORB for short. And every geologist, one of the first things they learn about is MORB. And they're chemically distinct and very well studied. In fact, we studied them because if there's been any changes or anything different from it, we actually can go back and track those changes and use it to make new ideas, new theories, and to look at the evolution of landscapes as it relates to the formation of these mid-ocean ridges. And of course, no picture of a seafloor spreading event with mid-ocean ridge basalt would be complete unless we had a nice photograph of a pillow basalt showing exactly all the features we've been talking about throughout this lecture, the pillow basalts, the MORB, and everything, all in a nice photograph. Just like subaerial volcanism, hydrothermal vents are also associated with submarine volcanism that we see in divergent plate boundaries. Mainly we observe this in the form of something called a black smoker or a deep sea vent. These occur where superheated water rises through the ocean floor. So of course, where's the superheated water coming from? It's the very same, or very similar, I should say, to what we're seeing with geysers, hot springs, and fumaroles. But those are happening in the subaerial environment as opposed to the submarine environment. So when the superheated water contacts the cold seawater, and by the way, I want to say this word superheated. This is at such high pressure that the water doesn't boil. It's far above 100 degrees Celsius. It could actually get over 400 degrees Celsius. When I'm talking about superheated, I mean superheated. It's extremely hot. But it doesn't boil at that depth. In some cases, it's actually believed to be a supercritical fluid within the plumbing system of the volcano. If you don't know what a supercritical fluid is, don't worry about it, or you can hit it on Wikipedia or something like that. But it's a very interesting phenomenon. When the superheated water contacts the cold seawater, dissolved minerals, especially sulfides, precipitate. So this happens a lot of times when you have something that is hot. It'll be able to dissolve a lot of stuff. And then when it hits something that's cold, it precipitates out because cold water can't hold as much stuff. It can't dissolve as much stuff as hot water can. So it supersaturates and it produces these minerals, forming a black plume in the water and a chimney-like structure around the vent. And so these are the black smokers. We see an image of one operating up there in the upper right-hand corner. You can see the black smokers coming out. It's actually not smoke. Those are mineral deposits. Those are minerals that are precipitating out of the water as it's flushing through. How does this come about? And again, here's the schematic. The water comes into these fractures. It gets close to this magma chamber, which could be extremely hot. Remember, basalts are much hotter than rhyolites are. So the water is able to come in, it gets superheated, and then it jets back up over here, and it leaves these big, massive sulfide deposits around it. And that's what you're seeing in that image. Now, there's another phenomenon called white smokers. They are cooler and they're further away. So instead of coming right up above the heat source, maybe this water is coming out somewhere off the screen. And as a consequence, it's cooler and it precipitates other minerals as opposed to sulfides that are white in color. Just as there's volcanism at divergent plate boundaries, which is prolific, there's also a considerable amount of volcanism at convergent. Remember, where convergence happens is where two plates are coming together. So this occurs at subduction zones where two plates converge and the oceanic lithosphere descends into the mantle, right? So the older and colder material is subducting beneath the younger and the hotter in terms of temperature material, right? So it's going to be younger, and it's going to have a higher temperature. And so when that happens, you wind up having the subduction of cold oceanic lithosphere into the mantle. When that occurs, you form something called a volcanic arc. And so volcanic arcs are slightly curved chains of volcanoes. We see an image of one right here. This is a Google Earth image that I captured. This is Alaska. This is Canada over here. This is Russia. And what we're seeing here is a trench moving over here. The Pacific plate is moving to the north and subducting into that trench and going underneath this set of islands right here called the Aleutian Islands, and then of course this is continental Alaska. So volcanic arcs are slightly curved chains of volcanoes. Here we see that chain of volcanoes. It goes up onto the continent over here and out into the form of an island. So the Aleutians, these are the Aleutian Islands right here. The Tongas and the Marianas are examples of what we call volcanic island arcs. So this is where the Pacific plate, which is an oceanic plate, is subducting beneath another oceanic plate, which is up here where the Bering Sea is. And that forms this chain of islands, this volcanic island arc. In terms of the Andes range, is an example of a continental volcanic arc. But we also have the same thing happening here in Alaska, where the volcanoes are continuing up into Alaska and then into Canada, and forming a very long continuous chain which transitions from continental into island arc volcanoes. We discuss this a lot more in my lecture on mountains, and so if you're interested in this phenomenon, by all means find that lecture, and I'll post it actually in the comments. Find that lecture and check it out. I think you'll really enjoy it. There is a third type of volcanism that occurs on Earth that is not easily explained by plate tectonics alone. It actually took a little bit of time for us to start working out what we think is going on, and it looks like there's these volcanoes that are occurring within plates that aren't explained by the edges running into each other, which is a very easy approach for plate tectonics to answer, but it's not so easy to answer why we would get, for example, the Hawaiian volcanic chain. It's right in the middle of the Pacific Ocean, and there's no subduction happening there. There's no convergence happening there. It doesn't easily explain it. And so what we have recognized is that there appears to be these phenomenon referred to as a mantle plume. And so we have a mantle plume that will ascend towards the surface. The surface manifestation of a mantle plume is what we call a hot spot. So we have a mantle plume rising up of hot material from deep within the mantle, almost like a blowtorch, pointed out towards the surface of the Earth. And what seems to be happening is that we have this formation of a hot spot where we have a large amount of concentrated heat and melting and volcanism that is associated with this. Large mantle plumes, which are dubbed super plumes, it's kind of fun to say that, are thought to be responsible for large basalt plateaus. Examples include the Hawaiian Islands, Yellowstone, and Siberian traps. And when we look around, we see that we have these very interesting locations where there seems to be these hot spots, right? So there's a hot spot here in Hawaii. We can track what seems to be a series of islands that are formed in this way. So when we look, for example, at the big island of Hawaii, here's Mauna Loa, here's Kilauea. Loihi, which is, by the way, a seamount that is forming off the coast of Hawaii, is the youngest of the volcanic chain. And what's happening is the Pacific plate is moving or dragging the volcanoes over the hot spot and creating new volcanoes, and at the same time retiring active ones. So pretty soon, when I say pretty soon, I mean geologically pretty soon, Mauna Loa is going to shut off, and Kilauea, which is already pretty active, will become far and away the most active, and then that one will shut off, and then Loihi will take over, and a new volcano will start to form off the coast here. And so we have these older, I guess you can call them extinct volcanoes at this point, like what we see over on Oahu, Molokai, and Maui. And then we have the big island of Hawaii where the active volcanism is happening. So it does turn out that plate tectonics explains the lines of volcanoes, but it doesn't explain the origins of the heat. That is something that is related to a phenomenon within the mantle itself. If human beings and volcanoes are going to have to coexist on planet Earth, and they're clearly going to have to, we're going to have to do something called volcano monitoring. And this provides hazard assessments for millions of people living in volcanically active regions, or someplace where a volcanic hazard could hit them. We were talking about lahars, for example. You don't have to be terribly close to a volcano for a lahars to impact you and possibly even take your life. So these are things that the public has to not only pay attention to, but many civil authorities study this information and disseminate that to the public. What do they look for? Well, the most notable changes in volcanic landscape that we can see are changes in patterns of earthquakes. For example, here is the big island of Hawaii, and here are the patterns of earthquakes that we're seeing here. The different colors represent different depths. So this is going to be Kilauea right here. This is a rift zone that's happening in here. And we can see these are relatively shallow volcanoes. This is magmatic activity happening within the volcano. Here's another set of earthquakes that are actually occurring right at the tip of at the top of Mauna Loa. And then over here we have deeper earthquakes that are happening. Is this the material that's coming up through the conduit from the mantle? You know, there's a lot of stuff that's going on here that could be interpreted from this diagram. We can look at inflation or deflation of the volcanic cone, or we could watch to see if the caldera floor is rising or falling. Changes in the amount and or composition of gases released from the volcano. That's another thing we can look at. A new tool that geologists have been using, especially for the last 30 years, but have become an invaluable tool for us today, is something called remote sensing. This is where we're using something that is far away, that watches, like a satellite or an aircraft, or in some cases even a drone, that can watch and look and monitor maybe the size of a mountain, the shape of a mountain, to see if it's changing its shape. If that's happening, we can get those types of detection or detect that kind of information and get it back to scientists who can warn people. For example, we could look at a mountain like this, and what we'll see here is this is the displacement in centimeters. This is an amount of change, or what we call ground deformation, that is occurring on this mountain. And here, this mountain has risen 15 centimeters relative to the background. So the background is still relatively flat. It's risen a little bit, but the top of this mountain has risen 15 centimeters. So that could be something that is extremely dangerous and needs to be watched. So before we conclude this nice little lecture, and it's been a fun time going through all this, I wanted to show you some exotic volcanoes as well. Subglacial volcanoes. These are volcanoes that are not subaerial, they're not submarine, they're subglacial. In other words, they're erupting into ice. And we actually have images of subglacial volcanoes in action right here. One off to the left and one off to the right. It's just fascinating stuff. And of course, we have extraterrestrial volcanoes as well. Io, in this image over here, Io is a moon of Jupiter. It is the most volcanically active body in the solar system, actually, that we've detected so far. And here we see a volcanic eruption happening live in this photograph right here. So over here off to the left here. It's just absolutely incredible. The largest volcano that we think exists in the solar system is Olympus Mons, which is on Mars. And this is a volcano that has very clear sets of calderas up on the top, where they're all nested one on top of each other. This thing is like the size of Arizona roughly, but here we can clearly tell that we have volcanism that is happening outside of planet Earth. And so understanding the volcanoes that is happening on Earth can go a long ways towards us understanding the solar system, other planets, and the origins of those landscapes. I hope you enjoyed going through this lecture on volcanoes and learning a little bit about volcanology. If I've helped you learn about volcanology, please support my channel and support me by hitting like. It really makes a difference. It really does make a difference. And it will help me bring more of these types of videos to you. I wish you all the best, and I look forward to seeing you in our next lecture.